Anyone in construction knows that cement is the lifeblood of a project, but not all cement is created equal. Today, we're going deep into the blueprint for quality. IS 269 for 33-grade ordinary Portland cement. Now, this isn't just some dry technical document. It's the absolute guarantee for the most fundamental material you work with. We're going to deconstruct exactly what the standard demands and why it's the critical line between a structure that endures for generations and one that doesn't. So, here's our game plan. First, we'll cover the big why, the standard's crucial role in safety. Then, we'll get into the nitty-gritty, the exact chemical recipe, and the tough physical tests every batch has to pass. From there, we'll follow the journey from the factory to your site, looking at quality control every step of the way. And finally, we'll wrap up with how you can verify compliance and what to do if the product just doesn't measure up. All right, let's kick things off with Section 1, the standard for safety. You can think of this as the bedrock for everything we build. So, what is IS 269 really? Well, you can think of it as the rulebook for 33-grade cement. It covers everything, from how it's made, to its exact chemical DNA, to how it has to perform under stress. The whole point is to eliminate guesswork, right? It ensures that every single bag you use meets a consistent, high-stakes, and totally verifiable standard. And really, this is the bottom line. It all boils down to one thing: predictable performance. When cement follows the standard, you get what you expect: safety, stability, and durability. But when it doesn't, you're introducing a massive risk. We're talking everything from minor cracks to, in a worst-case scenario, catastrophic failure. So adhering to this standard isn't just best practice, it is the absolute first step in quality assurance. Okay, moving on to Section 2, Cement's Chemical Blueprint. Now we're going to look under the hood at the precise recipe, the very DNA that defines high-quality cement. Every single component is meticulously controlled for a reason. Now, before we get into any specific numbers, we have to talk about something called the lime saturation factor, or LSF. This isn't just one ingredient, it's a critical balancing act. It's a very specific ratio of lime to other key players like silica and alumina. You see, getting this ratio perfect is the secret sauce for proper hardening, for how the cement gains strength, and for its stability over decades. And just look at the precision required here. That LSF value has to fall between 0.66 and 1.02. It's an incredibly narrow window. Think of it like walking a tightrope. If the value is too low, you get incomplete hydration, meaning the concrete will never reach its potential strength. But if you go too high, you end up with excess free lime, which can cause massive soundness problems down the road. Basically, you're building in a failure that might not show up for years. It's non-negotiable. And the chemical checks don't stop there. The standard puts strict caps on these three components. Too much magnesia can cause a delayed, destructive expansion. A high insoluble residue tells you the raw materials were poor or something went wrong in the kiln. And while a little sulfuric anhydride is needed to control setting, too much can lead to sulfate attacks that literally eat away at the concrete's strength. Each one of these limits is a specific safeguard against a known failure. Now, this number, 0.1%, might just be one of the most important in the entire standard. This incredibly low limit for chlorides exists for one reason and one reason only: to stop rebar from rusting. It prevents the corrosion of the steel reinforcement inside the concrete. And for highly stressed structures, like those with pre-stressed concrete, that limit gets cut in half to an almost undetectable 0.05%. It's all about protecting the structural skeleton from the inside out. All right, Section 3, the critical performance tests. Having the perfect chemical recipe is great, but it means nothing if the cement can't perform in the real world. This is where the rubber meets the road. This is it, right? The fundamental question for any structural material. But strength isn't just a single number, it's a process. It develops over time. The standard answers this question with a really clear, time-based series of tests that mirror exactly what happens on a real construction site. You see, the standard doesn't just ask for a final grade. It demands a clear performance curve. By testing it 3 days, 7 days, and 28 days, we get a full picture of how that cement is hydrating and building its internal strength. It's kind of like checking a patient's vital signs at regular intervals. It tells you if the process is healthy and on track. So at the 3-day mark, the cement has to hit a minimum of 16 megapascals. This early strength is absolutely critical for construction schedules. It's what allows for the timely removal of formwork so you can keep building upwards. This is the very first sign that the hydration chemistry is working correctly. Then, by 7 days, that strength has to climb to at least 22 megapascals. This second checkpoint confirms that the strength gain is continuing at a healthy rate. For a lot of engineers, this 7-day strength is a key quality control indicator. It helps them predict with confidence whether the cement will hit its final 28-day target. And here we are, the final exam. At 28 days, it has to meet or hopefully exceed its grade strength of 33 megapascals. This is the benchmark. This is the number that structural designs are based on. Hitting this target is the ultimate proof that the cement lives up to the promise on the bag, 33 grade. But check this out. This is arguably the most brilliant rule of all. It's not just about hitting the numbers. The strength must always be increasing. A batch of cement that hits 16 MPa at 3 days and 33 MPa at 28 days, but somehow dips down at the 7-day mark, is an automatic failure. This rule ensures the chemical reaction is stable and continuous, which is absolutely fundamental to long-term durability. Of course, strength isn't everything. The standard also controls 2 other key behaviors. First is setting time. You need at least 30 minutes to place and finish the concrete, but it has to set within 10 hours. Second is soundness. This test makes sure the cement doesn't slowly expand over time once it's hardened, preventing internal stresses that would cause it to crack itself apart. The maximum allowable expansion is a tiny 10 millimeters. On to Section 4, ensuring quality to site. So we've got this perfect lab-tested cement. That's great, but how do we make sure the stuff that actually arrives at your foundation is still perfect? For anyone on site, the markings on the bag are your first line of defense. This is the cement's ID card, and it provides a complete chain of custody. That batch number is especially critical. It lets you trace that specific bag all the way back to its production run and its test certificates. And that use no hooks warning, it's there to prevent tiny tears that let in moisture, which, as we know, is the #1 enemy of cement. And you might be surprised at how specific the standard gets about bag weight. Why? Well, think about it. Concrete mix design relies on precise ratios. If your bags are consistently underweight, it throws your entire mix off. Your water-cement ratio, your aggregate ratio, everything. This isn't about getting shortchanged a few pounds of material. It's about protecting the integrity of the final concrete. These rules make sure that a 50-kilogram bag is actually a 50-kilogram bag. All right, our final section, verification and compliance. This is all about the final checks. How do you test the material you've received, and what happens when it doesn't meet these incredibly stringent requirements? The standard lays out some very strict timelines. You've got 3 weeks from the day of delivery to take your sample, and testing has to start within a week after that. This makes sure the material is evaluated while it's fresh. And on that note, the shelf life rules are critical. Cement naturally absorbs moisture from the air. Requiring a retest after 3 months in storage acknowledges that its quality can and does degrade over time. It's a key protection against using compromised material. And let's be absolutely crystal clear on this one. Compliance is not optional. This is not a menu you can pick and choose from. If a batch fails any single requirement, whether it's a chemical limit, a strength test, or even just the markings on the bag, the entire batch must be rejected. There is no such thing as partial compliance. It's pass or fail, period. And that really brings us to the final thought. When you look at all the incredible detail here, the chemical formulas, the strength milestones, the package intolerances, it becomes obvious that IS 269 is so much more than just a list of rules. It is a blueprint for trust. It's a fundamental promise of safety between the manufacturer, the engineer, and the public. Meticulous adherence isn't just about compliance. It's about our professional integrity and upholding the promise that the structures we build are safe, durable, and built to last.